Today we're going to talk about the first part of Chapter 11, which involves atoms and their energy. Okay, so first let's review a few things about the atom. So let's look at the three main parts of the atom and their charges. So first of all, we have the proton, which is positively charged, and it's located in the nucleus. And along with the proton, we have the neutron, which is neutrally charged, or zero, and it's also contained in the nucleus. And then we have the electrons, which are negative and contained somewhere on the outside, but that's kind of all we know. And so we're going to look at, throughout this chapter, a lot more about the electrons. Okay, so if we review some of the models that we've discussed, we have the Bohr model, which says that electrons occupy specific orbits. Okay, and my circles are not quite perfect. So we have our protons and our neutrons in the center, and then it says that we have these electrons that are orbiting around. And we know that we can have 2 electrons in the first orbit and up to 8 in the sequential orbits. From the Bohr model, we went to the Rutherford model. This was when we talked about the alpha particles and how he determined that the nucleus was made up of positive charges and the electrons were somewhere on the outside. But we don't really know a whole lot about where the electrons are located, and that's kind of what we're going to talk about in this chapter. What their function is, where they are, things like that. Okay, so before we can talk about electrons, we need to talk about energy, because we know electrons are, for the most part, the source of energy in the atom. And so electromagnetic radiation is the transfer of energy from one place to another by light. Okay, and this can include, light can be lots of different things. It can be white light, like the visible light that we see, X-rays, microwaves, all different kinds of waves. Okay, and we're going to look at some properties of those. So before we talk about electrons, let's talk about wave characteristics in general. Okay, so wavelength, which is symbolized with the Greek symbol lambda, it's kind of like an upside down Y, is the distance, because of the length, between 2 consecutive wave peaks. And it's usually given in meters. Now this can be any point on the wave. It doesn't have to be peak to peak. That's just kind of the easiest spot to look for. But it's the length between waves. Okay, frequency, which is this V that has like a curved part to it, or sometimes we use an F for it, is the number of wave peaks that pass a certain point per given time period. So units here are hertz, or seconds to the -1, or 1 over seconds. It's basically number of waves in a certain amount of time, and so you would count the number of waves. It's kind of like if you're going into a baseball stadium, they count the number of people that go in, in like per minute. That's the frequency of people. Okay, and then we can take wavelength and frequency and put them together to get speed. This is how fast a peak travels through a given medium, and waves will travel through different mediums at different rates. It's kind of like if you try to look through a glass of water at something that's on the other side of the glass of water, it looks distorted because the visible light waves are traveling from air through glass, then water, then glass, then air again, and it distorts the wave, and so it travels at different rates. Okay, so let's look at a picture of comparing frequency and wavelength and speed. So this is a high frequency wave. Okay, as you can see, we have the same amount of time for both graphs. Let's say this is a second. Okay, so in this high frequency wave, we have 1, 2, 3, 4, 5, 6 waves going by in a certain period of time. And for the low frequency wave, we have 1, 2, 3 waves. So this is, less waves per same period of time. And if we're looking at wavelength, we said it was crest to crest, and so we could measure this as our wavelength. But like we said, it doesn't have to be crest to crest. It can be trough to trough, which would be the bottom part of the wave. It could be where it hits the x-axis. Now the only trouble with this one is you have to go to this point because they have to be identical points. Okay, so you wouldn't want to go to here. Okay, so that's wavelength. And so we've got frequency. This period is basically one wave. Okay, and so if we wanted to calculate speed, it'd be a combination of our frequency and our wavelength. Okay, and wavelength and frequency are going to become important as we talk about electrons. Okay, so like we said, different types of electromagnetic radiation exist, and they each have a different wavelength. So sometimes we can talk about light also behaving as a stream of particles of energy versus a wave, and that's kind of the discussion that we have with electrons. We say that they kind of behave as a wave, but they also behave as a particle, so they have both of those properties. Well, particles of energy or packets of energy are called photons, and we're going to talk a lot about these photons. So the longer the wavelength of light, so the longer the wavelength, the bigger the distance between waves, the lower the energy of its photons. Red light has a longer wavelength than blue light, and so we would say that it has less energy. And the way that I always remember this is when we look at a picture of this, we'll explain it. But blue light is closer to ultraviolet light, which is sunlight, and I know sunlight has lots of energy. So that's how I kind of remember the difference between red light and blue light, which is going to become important. Okay, so here's a picture of the electromagnetic spectrum. Down here you can see we have radio waves and TV waves, and their wavelength is very long. Okay, and so here's their frequency is also very small. Okay, so then we've got microwaves, infrared, which is like a heat lamp, and then here's our ultraviolet. But before we get to ultraviolet, we've got visible light. Okay, it goes right about there. Okay, and so you can see red wavelength is 700 nanometers. Violet wavelength is 400 nanometers. Remember, nanometer, 1 nanometer, is equal to 1 times 10 to the negative 9th meters. So although they are really tiny, red has a longer wavelength, so they have less energy. It also has a smaller frequency, less waves in the same period of time. Blue and violet light have a higher or a smaller wavelength, higher frequency. And then we're getting into ultraviolet, X-rays, and gamma rays. I mean, look at the wavelength on the gamma rays. They're very short. And that's because gamma rays and X-rays are more dangerous to your body. When you go to the dentist, you put on the lead apron because they don't want the X-rays to penetrate your whole body. Whereas radio waves, TV waves, microwaves, these pass through your body all the time and don't cause any damage. All right, now let's relate this a little bit to the atom. Okay, when atoms receive energy through electricity, heat, whatever, they get excited. And then those electrons move, and they release that energy as light. Okay, and so the way that the energy gets released is through a photon, through that packet of energy that we talked about. And the amount of energy in that photon corresponds to the amount of energy change that the atom has experienced. How much energy did it gain? So a high energy photon that's released is going to have a short wavelength, and we know short wavelength means either blue or violet, okay, or other types of waves that we can't actually see. We're just talking about the visible light spectrum. We'd be talking about blue or violet light. A low energy photon has a longer wavelength, so we know that this means red, orange, that's that part of the spectrum. And so we can look at the colors that are given off and relate that to the amount of energy. Okay, so now let's look at how this relates more with an atom through energy levels. Okay, so we know that we give an atom energy, and it goes to what's called the excited state. Okay, it's been given this extra energy, it's now excited. Some or all of that energy is going to be released by emitting a photon, this packet of energy. Once that energy is released, the atom moves to a lower energy state, the lowest energy state being the ground state. And so that's when it's closest to the nucleus. And the reason we call it the ground state is because electrons are constantly fighting that attraction from the nucleus. And so if they're given energy, they're able to jump away from the nucleus. But once they lose that energy, now the pull of the nucleus is causing them to become closer. Okay, so let's look at a picture. Okay, so here we've got our energy being given to the electrons, or to the atom. And so then it becomes excited, and then you've got the electron jumping an energy level. It was originally here, and it jumped here. And so we would say it's in the excited state. Okay, eventually what's going to happen is this energy is given off. So this would be our photon. Okay, and this is what we're seeing as light. Okay, we can only see the light when the energy is given off, not when it's given to the atom. Thing is, these sometimes occur almost simultaneously. Okay, so as that energy is given off, now the electron loses energy. Now it jumps from this shell or this energy level to a lower energy level, and we say that it's, a lower energy state, maybe sometimes the ground state, but it's not in the excited state anymore. And so basically, these are the two steps that are happening. Now, electrons can jump more than one level. They don't always have to go back to the ground state, and that's determined by the amount of energy that's given to the electrons. So let's look at hydrogen as an example, because hydrogen is one of our simpler atoms. If we give a hydrogen atom lots of energy and look at the photons that are emitted, we don't see a rainbow. We see certain lines of color. Okay, so we don't see everything. We see very specific segments. Okay, and what this means is that only certain photons with certain amounts of energy are being emitted. And so we only have these certain energy changes that are occurring. Well, how are these energy changes occurring? Well, this tells us that because we're only seeing these very specific jumps, these very specific amounts of energy in the photons, that hydrogen must have discrete or separate energy levels. Okay, and that relates back to our Bohr model. Having these jumps of energy, okay, each one requires a certain amount of energy to jump levels, and that relates to our photons. Okay, so this is what we're going to do later this week. We've got a gas tube, okay, filled with an element gas, hydrogen, neon, argon, whatever it might be. And we've got these little electrodes at the top and bottom. Well, this is kind of like a fluorescent bulb. We excite the atoms, we give them energy, okay, and that energy passes through the bulb, exciting those electrons, and they then jump to higher energy levels, and when they jump back, they give off that energy as a photon. And we look at that energy that's given off, that light, through a prism or a spectroscope, and that breaks light up into its visible components. And so then we can see these very specific, discrete units of energy. Okay, and the cool thing is that every element has its own, what we're calling atomic spectra. Okay, and so it's kind of like a fingerprint for the atom. Okay, so here are some more pictures. This would be sunlight. Okay, so as you can see, we're getting all the colors and they're all kind of meshed together. Okay, but if we look at some specific elements, hydrogen, helium, mercury, uranium, okay, you can see we've got these very discrete segments or packets of energy being given off. Okay, here we've got a low energy packet because it's red. And here we've got a high energy packet because it's purple. And since each element has its own atomic spectra, astronomers can use really high-powered spectroscopes to look at stars and match up what they see in their spectroscope to things like this and determine what elements are present in stars, even though they're really far away. So it's very cool. Okay, so we are going to be doing a lab looking at this, and then we'll also be working on homework. Have a good day.